Okay, so this video is picking up where the last one left off. What I want to do is go through the configuration of the scope because it's pretty tricky. Not tricky in the sense that it's difficult, it's just that if you haven't used these scopes a lot, there's a lot to learn. So I played around with the scope a lot yesterday, and still I wouldn't consider myself an expert on this scope by any stretch of the imagination. But let's say you log into the computer and somebody had been using the scope prior to your lab, and they left it like this, right? Or they left it in some state that you need to fix. So here's my quick routine that I go through. You can go just click on preset, sort of sets it up to some preset that somebody else has stored in here, but you can see that channel 1 is now turned on, channel 2 is turned off, the I2C information has disappeared, and so on. Then I like to just click on auto set. Okay, and then you should go in and verify that the channels are set up correctly. So let's click on channel 1, set it up for DC. Click on menu actually, so you can see everything at once. So I want it on DC, I want the full bandwidth, and where is it? I have to scroll down. Probe. Make sure it's set to 10:1. These are 10:1 probes that are installed right now. And that should be it. Don't mess with the adjust or anything like that. So that channel is now set up. You can see it's DC 10:1. We'll fix the scale a bit later. Let's do the same for channel 2. I just turned it on. And I'm going here to menu for it. Oops. Menu. And it's DC, full bandwidth, probe. It says 10:1. I'm just showing you where it is here. 10:1. Great. Set. So my two channels are set up well. Back here to auto set. And it'll space the channels out nicely for me. And right now I have the firmware running on the microcontroller. Maybe I should back up a step here and just point out that you should get the code, get the project, recompile it, so rebuild. Shouldn't get any errors or warnings. And flash the firmware onto the target device. And then when you do that, if all goes well, you'll see these waveforms. So make sure you do that first. Actually, I should have started the video with that. And let's zoom in here and see what's going on. I'm clicking on scale. I'll just mention here that you can click on the button to flip from coarse to fine mode. Unfortunately, it doesn't, as far as I can see, it doesn't tell you what mode it's currently in, which is kind of annoying. But then you zoom in or zoom out depending on which way you turn this. So now I'm zooming in, and you can drag the screen with your mouse so you can see things. Okay. So what we're looking at here is a clock in the green, and we're looking at the data line in yellow. It's important to be able to distinguish the two because we're going to set up an I2C protocol channel as well, and you need to tell it which scope probe is connected to the clock and which scope probe is connected to the data. Okay, and I'll be asking you to look in detail at some of the fine points of these waveforms. Let me go through a few of them now while I'm going through the use of the scope. I'm going to zoom in a bit more. I always get that backwards. Okay. So a few points here. This region, you'll notice that both of the I2C lines are high. So that's an idle bus, and we expect both of the lines to be pulled up to VDD in that case. Then we see a start condition being asserted. And what does that? Don't forget that when the bus is idle and the SDA line gets pulled low while the clock is high, that signifies a start. And then the clock will start running. You might be wondering what these glitches are. Well, the two pins for SDA and SCL, they're side by side, and the scope probes are side by side. So you're actually seeing crosstalk here. When that fast falling edge occurs, we get an injected current or voltage into the clock line. That's why we see this. Okay? And that happens at every clock edge if you look. The other thing you'll notice is that there's definitely some low pass filtering happening here. And that's because of the capacitance on the I2C lines. And that ultimately will limit how quickly you can drive those lines with the current resistors that are installed for the pull-up resistors. You can go through these analog waveforms and you can decode exactly what's going on here, just like I did in class, just like I did in my live stream video. So the trick is to always sample the value of the SDA line when the clock is high. As an example, clock is high here, we see SDA line is high, so that's a 1 that was transmitted. Here, the next clock pulse, it's a low, so that's a 0. Then we have a 0. Then we have a 1. Then we have a 1. Then we have a 1. Then we have a 1, and so on. And you can go through that clock pulse by clock pulse, and you can figure out exactly what's being transmitted here. So that takes a while to do. It's a little bit boring and monotonous, but it can be done. So if you didn't have access to a scope with built-in I2C protocol, you can do this. The other thing that the analog scope is very useful for is to find glitches that occur during sampling times. So right now it's pretty clean, the signal, at the sampling times, which again is the high part of the clock. But let's say, just for example, there was a big glitch right here, and it drove this low at this point in time, just when I want to sample. Well, you wouldn't see that unless you looked at it in an analog waveform view. Okay, so let's zoom back out. Way out here. Now you should be paying attention to things like how long does the data transfer take? I haven't explained yet what's being transferred, but we'll look at that in a bit. So you can measure that, you can put some cursors down. Where are they? I want to measure horizontal, so click on that. And where are my cursors? This is what I mean. See, I just did this not even an hour ago, and still I forgot how to do it. So there's one cursor, and then you get confused. Where's the other cursor? Well, the other cursor is hidden over here by the menu, which is kind of a bad design, isn't it? So you drag that over there, and then you can get the delta. It's about 480 microseconds. And you could zoom in on the individual clock cycles and measure them as well, of course. And then you could confirm what the bus clock is operating at, which I won't tell you because I think that will probably be one of the lab questions. Okay, so that's for the analog waveform, and you guys can play around and figure out all kinds of neat stuff you can do with that. I want to add into this a protocol. So there's a few ways to access that. I'll show you just a quick way. You can click on this icon here on the scope. Click on protocol, and you don't want SPI, you want I2C. So you have to click on that, and then this crazy looking thing shows up at the bottom with a lot of red. And the reason it's red is we're going to have to fix the clock and data lines because they're actually reversed. It won't necessarily be the case for you. It just happens that the way this was connected, they're reversed. So I'm going to go to menu, and where was that? I think it was under configuration. Yeah. So you see SCL it thinks it's the yellow waveform, and SDA it thinks it's the green waveform, but they're actually the opposite. So click on the yellow, change it to C2. Click on this one, change it to C1, and close that window. And now we're good to go. Let's make some space on my screen here. Drag this over this way, and let's zoom in a bit. I always do it the wrong way. Okay, that's nice. See, we're getting this thing keeps changing here. Personally, I find that kind of annoying. So you can change that. You go click on the I2C, go to the menu, and display setup, and display, change it from ASCII to hexadecimal. You can put it to whatever you want, but I like it in hexadecimal. And there we go. So it's color coded. There's and I'll just read for you what this is saying. This is writing address 4F, so that would be the address of the slave. And we'll have to zoom in to see a bit more of the features here. Let's do that. Actually, I might as well show you the better way to zoom in. So I can leave this on the screen, and I can click on zoom, if you can believe it. It brings up these cursors now. And then I can change the amount of the zoom. Oops. Didn't want to do it that way. How do I do it? Now I can't remember. There's a zoom scale here. Is it the horizontal? Zoom scale. There we go. So I'm just going to move that around. I'm going to zoom way in. Okay, that's about where I want it. Now I can take this white box at the top and I can move it where I want. See that? And then the box at the bottom, or the waveforms at the bottom, are zoomed in versions of the one at the top. It's kind of neat. It's kind of useful. So I'm going to go look in this area. So remember I said there was a start condition asserted here and then things started to take off. Well, I noticed that the protocol software module in the scope was able to determine that, and then it looked for the address. So it got the address, and if you decode these waveforms, you should get this address. And then it says, okay, we're going to do a write. Why is it a write? Well, you look at the clock. Remember, the clock is the green waveform on my scope. The clock is high, and at that point in time, the SDA line is low. Remember, the write is active low, so it's going to be a write. Then we get an acknowledge. That's what this green box is, with the A is. That's because the slave pulled the line low. That's kind of neat. Let's keep going here. You got interrupted there just briefly. So anyway, back. So now we're looking at the data. So you can decode the data. It's 00 hexadecimal, and you should be able to see that in the waveform. We see another acknowledge, right? So this was a write. We wrote that to the slave. The slave acknowledges. Let's keep going. Then we're going to do a read. So this is a address read, and the address is 4F in this case. Make sure that corresponds to what you expect it to be. You'll remember in the code, the C code, or if you look in the code, that's not the number that's there, but this is correct. You'll just have to understand why the C code is written a little bit differently. This time we're doing a read operation, and it detects that. Then we get an acknowledge from the slave in this case. Then we get 2 bytes of data. The first byte is a 3C. It's changing, right? It's changing because the temperature is changing. Then we get another byte of data. It's also changing. Then we get a NAC. That's what this red is. And it's a NAC. Remember, I went through that in the live stream. We get a NAC, and that's generated by the master in this case. And then we get a stop condition. Okay, so hopefully that all makes sense to you. Turn off the zoom, because I want to show you a few other things. So this is let's look at the code, see what's happening here in the code, and see if it corresponds to what we're seeing on the screen. In the code, I do a write, and then I do a read. And I write 1 byte, and I read 2 bytes. And that's exactly what I see over here. I do a write, 1 byte, I do a read, 2 bytes. And there they are. Isn't that cool? I think that's so cool. But this is happening in a loop, right? So if I zoom out far enough, I should see more writes and reads. So let's see if that's true. I'm going to turn this on coarse mode, I hope. Again, it doesn't tell me what mode it's in, which is ridiculous. And I'm going to zoom way out. Oh, that's too far out. Look, I get 80 seconds on here. Like, it's a bit ridiculous. I'm looking for something in the order of 100 to 200 milliseconds, right? Yeah, there we go. I see a few on the screen now. So let me go back here. There we go. So what's the spacing between? So each of these, if you zoomed in, would be a couple of data frames, right? And what's the spacing in time between them? That's kind of interesting to look at. So you guys should measure that. And again, you can measure. You click on measure over here. And you go to horizontal. Then you have to drag your cursors around. Where are my cursors? Put them back up here. And then drag this guy over here, let's say. And the other fellow's hiding. Maybe I can grab him. Yeah, I got him. Put that one there. And I get 116.5 milliseconds, give or take. But the code says 100 milliseconds. Maybe that's something I'll ask you guys about as well. Why is there that discrepancy? It's normal, but why does it exist, right? And what else? Well, I'm gonna ask you to do a bunch of things, but this is the basics of using the scope. Oh, there's one other thing I need you to know how to do. I'm gonna show you that right now. So I'm gonna zoom back in on one of these guys. One of these days I'll get it right. I'll turn that thing in the right direction. Okay, so now I'm back here at a zoom version. And I'm going to show you how to trigger differently for the I2C. It's really cool. It's almost like the logic analyzer. So, actually, I'll show you two things while I'm at it. There's this thing called the bus table. I can click on that, and I get this, and I can move this up almost like in Windows now, and I can get multiple frames shown for me. So it's showing me that there were 2 frames, and they can be separated in time by quite a large margin. And it'll still find them and build them into a table. And you can even get it so that if I change this and I added some code that did a whole bunch of reads and writes, I'd get multiple frames down here. If you get multiple frames, a little scroll bar shows up here, and you have to scroll up and down. So this is showing me that there's a write sent to address 4F, length of 1, data was 0. There was a read. ID again, same slave, length of 2, and this is changing because the temperature is changing. You can see that over here. It's still capturing the data using teraterm. Okay? So far so good. I want to show you how I can trigger on the address and how I can trigger on the data. So you can get to a lot of the functions in multiple ways. You can click on trigger, for example. Brings this up. So right now trigger is on auto. Trigger type is serial bus. Source is I2C. And I can set up the trigger. I can click on that. Oops. Click on that. And, oh, that's not what I wanted. Now I'm having a brain burp again. Where was that? It's on serial bus. No, I don't want edge. I want the serial bus. That's correct. Go back here. Give me a second. See, I'm telling you, you can get messed up. Oh, okay. I had the right screen. I just didn't clue into this being there. So you go to trigger setup, and then I2C trigger. It's by default it goes to the start, so the start condition. But you can change that. You can click on this and say, okay, instead I want to trigger on a stop condition or a restart condition. We haven't really discussed that in class, but there's also a restart condition. But let's do address and data. Sometimes it disappears on you like that. So this is pretty neat. And again, it's sort of like the logic analyzer. I can tell it that I want to, for example, trigger on a certain address. So, and on a read, I can change that to write if I want. So let's trigger on the first read, and just for practice, we're going to change this to 4F. Good. So now it's set up. And I was playing with this before, that's why this is set up like that. And I'm going to turn off the data. So it's not going to be triggering on data. I'm going to turn this off. So put X's. So any data, but it has to be a read at 4F. Let's see what happens. And let's turn off the menu so we can see more. And I'm also going to turn off this, this table here. And I'm going to drag this over so the full frame is here. And did it trigger on a read at 4F? Let's turn off the cursors too. It's definitely triggering. What's it triggering on? Let's stop it and start the trigger again. Okay, this is what I'm looking for. This trigger, this is showing the trigger point. So why is it not over there? It's triggering on the data. Let me check that again. I guess maybe it has to trigger on the address and data, not just the address. I thought I had it set up before, so it was only looking at the address, but maybe I was fooling myself. So I guess that's normal. It's looking for this address, and then it looks for that first byte of data. I guess I can prove that if I go here. So right now it's triggering at the end of the data. So it found the address on a read, found the data. If I tell it to look for 2 bytes of data, then we'll know if it's correct. So I'll look for 2 bytes of data of any format, and let's see where the trigger point moves. Yeah, so that's true. See, the trigger point moved over here. So it looked for the address, the first byte of data, and the second byte of data. And I can trigger on a specific bit of data. So if I wanted to, I could trigger when the temperature hits a certain level. It's kind of neat. Okay, so what else? That's about it. I mean, there's so much you can do with these scopes. It's amazing. I guess I could show you how to trigger on a specific data. So let's go back here, see what the data is at now. It's climbing, so it's 2A. Let's trigger when it gets to it's climbing so fast. So let's trigger when it gets back down to the 34 range, just for fun. So go here. I want the first byte to be 31. 3 and a 1. Okay. So it's not triggered, right? It's not triggering. So that temperature is going to have to fall back down to what it was before. Okay, it's getting there now. It's falling, falling. I should see this trigger. When it's steady on the screen, I'll know it's triggered nicely. Oh, did you see that? Okay, I'm going to hit run stop. So now I've got it. I've got it. See? 31. Isn't that cool? So you could probably get a question like that also in your lab to trigger on a specific condition. And that's about it. I've rambled on enough. Watch this a few times though, so you can see what I was clicking and how to set it up, because otherwise it's It's difficult to do sometimes, but practice makes perfect, right?